Question 4, and we're spray painting a chair. We've got our spray gun and we are charging our paint droplets. The key thing with this part is that it says electrons are moving along the charged wire towards the nozzle to charge the paint. Straight away you're thinking electrons are negative, so the paint is going to be negative. Chair is connected to earth, and we've got to work out when the droplets get near the chair, what charge will the droplets have, what charge will the chair have. The paint droplets have got to be negative because they've got a load of electrons on them from the wire, so it's going to be either A or B. Now when these negatively charged electrons get near this chair, and this chair crucially is connected to earth, what will happen is that the negatively charged electrons will repel the electrons inside the chair, and those electrons in the chair, because they've got this wire to earth, they can actually escape the chair, they can go into the earth, they can flow away and be free. So when this negatively charged cloud of paint droplets gets near the chair, it's going to repel the electrons in the chair, they're going to flow away into earth, and what you'll be left with is a chair that's got more protons than electrons. Now it's lost some electrons, so it's going to be positive. So you're going to induce a positive charge on your chair. So the paint droplets will be negative, the chair itself will be positive. It's got to be B for that one there. Now if we move on to our second part, part B, we've got a bit of glass and we're rubbing it with some silk, and the glass has become positively charged. We've got to explain how rubbing the silk charges the glass. Well, it's kind of a two-step thing really. You're going to explain that when you rub them you're using friction. There's one mark straight away. They put friction in bold in the mark scheme, in fact you'll be able to see it there, so you had to use that as a key term. And as a result the charges are going to move. So we're told that glass has become positively charged. We must have lost electrons off that glass then, mustn't we? So the electrons have been taken off. So one mark for saying friction, one mark for saying the charges move. The silk is also charged. We kind of alluded to that earlier, didn't we? So if we're rubbing the glass and the glass is becoming positively charged, that is because we're taking the electrons off the glass. The electrons have gone onto the silk, so the silk is going to gain a negative charge. So you say one mark for saying that the silk is negatively charged, and one mark for saying it's because the electrons have been transferred onto the silk. And for this next bit we have to describe a situation where separation of electric charge can create a spark. Now there's all kinds of different situations that you could talk about. There are several that are mentioned in the book. So some of the time, one example for example, it would be when we've looked at refueling planes. So that came in the dangers of static electricity section. If you've got a plane and you're trying to refuel it, imagine here's my plane, looks pretty plane-like to me. We bring our wire closer and closer to, or fuel pipe closer and closer to the plane in order to refuel it. If this has got a big charge on it, then the charge can jump across the air gap and into this cable. If you've got a big spark, that's obviously not good because it can set the petrol on fire. It's not actually petrol, but we'll go with the fuel for the plane, I guess you could say. So if you were to pick that example, remember it's a 2 marker, you would be getting 2 marks for saying the spark, so where the spark's going between, and sort of giving the situation, I guess. You could also mention the spark that you get between you and your comb or your clothes. You could talk about sort of taking your jumper off and it rubbing across your hair to transfer the charge that way. Then if you get enough charge separation, enough charge building up on those things, you can get a spark there. That's when you take your sort of woolly jumper off and you can hear that kind of crackling going on there. That's electric charges jumping. You could also talk about lightning. So if we have enough charge separation building up inside a cloud, then you get enough potential difference eventually for the electrons to jump, and that's how we get lightning. So all of those different situations. You want to avoid talking, however, about sparks jumping from a source of voltage, I guess you could say, that isn't static. So all of these are examples of static electricity. in the mark scheme specifically they say to ignore between plugs and sockets or between jump leads, because you've got a power supply in both of those situations. So we're really just talking about when we've sort of created a separation of electric charge. That's a static effect rather than through a power pack or through a car battery or something along those lines. So we move on, the final part of question 4, and it's a calculation, and we have some dodgy units in there that we're going to need to change. We can't put those into an equation. Remember, the only time you're ever going to see a unit that you can put a dodgy looking unit into equation is mass, because mass unit is the kilogram. But all of the time you see kilo or giga or mega or micro or any of these things, you're going to need to convert it, with the exception, you may remember, of the pressure equation in question 1. Although I should point out that if you did convert it for question 1, it wouldn't actually give you the wrong answer, it wouldn't be a problem. Anyway, we're waffling, let's get into it. I've got a charge Q of 0.22 microcoulombs. So straight away I'm thinking it'd be good to convert that, so that's going to be, you could write that as 0.22 times 10 to the power of minus 6 coulombs. You could do it that way. Every time you see a micro, that just means times 10 to the power of minus 6. Or you could think of it as, we need to divide this by a million, because micro means divide by a million. Either way, 0.22 times 10 to the minus 6, that will give you 2.2 times 10 to the minus 7 coulombs. Let's stick it in the calculator. Either way, that will give you the right answer. And we've got a time of 2 milliseconds, so that's 2 milliyears times 10 to the minus 3. Or alternatively, you can think of it as divide by 1,000. So that's going to give you 0.002 seconds. So we've done our unit conversions. We're good to go on those. The last thing we have to do is put the equation together. So we need an equation with current, charge and time. That's going to be Q equals IT. Charge is current times time. We're trying to work out the current. So the current I is going to be, well, you need to divide both sides by T. And with Q over T is equal to I. So you're going to take your charge, 2.2 times 10 to the minus 7, divided by your time of 0.002 seconds. And we'll see what that gets us. So 2.2 times 10 to the minus 7 divided by let's stick the whole thing in, 0.002. Calculator buttons are a bit dodgy. We end up with 1.1 times 10 to the minus 4. No rounding or anything needed for that. It's just 1.1 times 10 to the minus 4, and it's a current. So of course the unit for that will be amps. So we have 1.1 times 10 to the power of minus 4 amps. Now I haven't put the substitution in there. If I was doing the exam, I'd have written out 2.2 times 10 to the minus 7 at the top there, and 0.002 at the bottom there. But there you go. It says, incidentally, on the mark scheme, power of 10 error only loses 1 mark if the rest is correct. So if instead of going 1.1 times 10 to the minus 4, you might have 1.1, or you might have 110, or 1.1 times 10 to the minus 17, or whatever weird and wonderful thing you've got from your calculator. If that's happened, it's because something weird has fouled up earlier, but everything else is fine, so you'd only lose 1 mark on that one. And that is question 4.